Hello, everybody. Welcome to the Coopersmith, a crash course on Earth Science, Essentials of Earth Science. This is a course that will study things about essentially two major topics, meteorology and geology. In other words, weather forecasting, weather systems, which we're actually going to cover second, and geology, which has to do with rocks and minerals and things like that. It will be assessed with a final exam. This is from the course syllabus. You don't need me to read that. The course descriptions and the course goals, again, are going to be dealing with those two major subjects. We're going to be based on this textbook, the Tarbuck, Lutens, and Tassa textbook, which you can get at these links. But what I'm going to do is I'm going to take you through the materials and just give you kind of a little bit of a refresher course on it. We're going to discuss a little bit about the various materials that you are going to be expected to know for this final exam and for the course in general. So the first thing we're going to look into is the scientific method and scientific inquiry. Scientific inquiry is the idea of trying to make sure that things work. First of all, trying to develop what are called hypotheses, which are educated guesses about the way things work, and then going about testing them. Scientific inquiry is the way that is accepted for processes to develop new scientific knowledge, and it can be used to discover any pattern, insight, knowledge, etc. Facts are collected through observation and measurement. That could be facts like temperature, size, color. All these things can be actually observed and measured. That's how facts are created. Then once you've collected the facts, or really even before you test you collect the facts, you can develop a hypothesis. A hypothesis is an untested explanation. It's really kind of an educated guess, where you think you might know what's going on, why something grows tall, or why something bounces off the wall, or why something turns a particular color in a particular temperature, but you don't really know. You may have more than one hypothesis that explains a set of observations, so the way you decide, A, whether your hypothesis is correct, and B, whether there are other hypotheses that might be relevant, is you test it. And the way you test it is by experimenting and observing. You watch something and pay careful attention to what happens to it when you test it in order to gain information, and you experiment. You can conduct a test in a controlled environment, and the tests should be repeated numerous times for accuracy. Just to give you an obvious example, if you're testing which pain medication or which, let's say, headache medication is the best in relieving pain, well, what you can do is you can make a hypothesis that Advil is going to be the best, or you can make a hypothesis that Tylenol is going to be the best, and then you could experiment and observe. You could take 20 people with headaches, give 10 of them Tylenols and 10 of them Advils, and see which one has a higher success rate. Obviously, you want to experiment as many times as possible, because the larger volume of data you get, the more information you get, the more likely it is that your conclusion is correct. Then finally, once you have observed and experimented and done it enough times, you can develop what is known as a theory. A theory is a well-tested view that explains scientific observations. It confirms the hypothesis, or it could confirm that the hypothesis is wrong. Either way, the result of your observations, the result of your measurements, the result of your experiments has indicated that something is true or that something is false. And if you confirm one hypothesis, so competing hypotheses need to be eliminated. So if your experiment confirmed the idea that Advil is the best, well then it eliminated the theory, or at least the hypothesis that Tylenol was the best. And scientific theory is knowledge which is widely accepted by the scientific community. If you develop a theory, or if you think you have a theory, what you usually do is you submit it to a journal, maybe you write an article about it, submit it to a journal, have other scientists look over your methods, and hopefully if they approve them, the general community will accept your conclusions. And of course, a theory is subject to change if new facts come up. So, in the scientific investigation, just to this kind of a recap over here, you raise a question about the natural world, whatever, and my example was a little bit not quite like the natural, not really exactly natural, more like artificial, but it could be about any question that you want to answer. A question could be about which object is going to fall faster, or which kind of airplane is going to be more aerodynamic, which kind of car is going to get better gas mileage, whatever your question is. Collect data, factual data that relates to the question, develop a hypothesis, or more than one hypothesis, undergo observations and experiments, test your hypothesis to make sure and see if it works, These experiments should be done with proper conditions, which means everything else should be held constant. To give you my headache example before, if you gave, let's say, for example, you have 200 people with headaches, 100 of them you give Tylenol to, and 100 of them you give Advil. You want to make sure that in every other respect they're the same. If one group, the one that you gave the Advil to, had loud music in the room, then, well, obviously the fact that they kept their headache might be because of the music and not because of the Advil. So obviously you want to make sure that everything else is the same, which means you want to control for it. You want to establish a control to make sure that everything except for the thing that you're testing remains the same. Based on your experimenting, a hypothesis can be modified, accepted, or rejected. You share the results, and if it gets accepted, it may become a theory. Okay, now we're going to shift gears a little bit and get kind of into earth science. And the first issue is the layers of the earth, sometimes known as the geosphere. And there are 4 layers of the geosphere. Geosphere means the earth, the layers of the earth, starting from the middle of the earth, working your way all the way out to the ground itself. In the center of the earth, you have what is called the inner core. The inner core always means the middle, like the core of an apple. The inner core is made of metal, it's made of iron or nickel, it's solid, and it's the earth's innermost layer, and it has a hot temperature, a very, very hot temperature, thousands of degrees. The only reason why it's able to remain solid, even though, as we'll see in a minute, the outer core is actually liquid, is because there is tremendous pressure that keeps it as solid. If you would take metal at that temperature and put it on the surface of the earth, it would be a liquid. But because there's so much pressure squeezing it together, it stays a solid. So the inner core is made of metal, it's solid, it's the Earth's innermost layer, smack dab in the middle of the Earth, and it only remains solid because of very, very, very high pressure. Something like 4 million times what the pressure is on the surface of the Earth, which is where we live. Outside of the inner core, you have the outer core. It's also made of metal, same metal, iron and nickel, and this time, on the other hand, it's liquid. And the reason why it's liquid is because it is very, very hot, and there's not quite as much pressure as there is in the inner core, which would otherwise turn it into a solid. If the core would be made of rock, it would also be liquid. So, generally speaking, rocks actually have a lower melting point than metal, which means it's much easier to heat them up and melt them. And so the inner core, the outer core, is liquid even though it's metal, which has a relatively high melting point. You have to heat it up because it's extremely hot, and it doesn't have as much pressure as the inner core. So the idea is both cores are made up of essentially the same metals, nickel and iron. The only difference is that the inner core is solid and the outer core is liquid. Then you have the outer layers, really the rocky layers. Outside of the inner core, you have the mantle. The mantle includes what is called the asthenosphere, which is the outer layer of rock. It's solid and it's made from rock. And then on top of the mantle, you have the crust. The crust is the lithosphere, by the way, just means the rocky part of the Earth, which is really the mantle and the crust. And it's made from rock, and it's the thinnest layer of the Earth. Just to give you a little bit of a diagram, if you look over here, you can see the crust is this tiny, tiny, tiny little layer all the way on the outside over here. That's where the oceans and the continents sit on top of. We only deal with the crust. I mean, maybe we could dig deep enough to get to the mantle, but generally speaking, everything that we do is on top of and in the crust. Underneath the crust, you have the mantle, which is a very wide layer of rock, and then in the core, in the middle over here, you have the inner core and the outer core made of liquid, and the inner core made of solid, but all of it really made of metal. And again, if you look over here, the kind of a cross section, you have the crust on top over here, the oceanic crust beneath the ocean, the continental crust beneath the continents. You have the lithosphere, which is the rocky part, and if you go further down, you have the asthenosphere, which is part of the mantle, which is, it's solid rock, but it slides around a little bit, and then you have the lower mantle down here, and beneath that, you have the core. Chapter 2 is all about matter and material. Matter means stuff. Everything, every physical object that can be moved and seen and dealt with is made of material. It's made of matter. It's really liquid, solid, gas. It's all considered matter. Now, the Earth itself is made up primarily of minerals. What minerals are rocks, but they're based on one substance. If you take many minerals and you move them together and you squish them together and make them one big thing, then they're called rocks. But mineral just means one substance. For example, if you take quartz and calcite and a few others and you put them together, you might come up with a rock called granite. But there's no inherent difference between them, except that a mineral is a single substance and a rock is many substance. Minerals can be identified. People who are geologists, people who look for different types of materials in the ground, have to be able to identify them, and minerals can be identified by physical properties. They also have predictable chemical composition. Different types of minerals, things like quartz, calcite, diamond, graphite, these are all minerals, and they can be identified by various physical characteristics and chemical characteristics as well. A few things that identify or that characterize minerals in general is that they have an internal crystalline structure, which means essentially that they're solid and they're consistent throughout. They are solid. The atoms, which are the basic building block of all matter, are bonded together in regular, repetitive internal structure, which means it's pretty consistent throughout. And regular shaped minerals, which means minerals that are not jagged all over the place, minerals that are round or square or something like that, are considered crystals. Atoms, as I just mentioned, are the basic building blocks of everything, all matter. There we have a periodic table which I'll skip to and we'll come back. But this is just a periodic table of the elements, which is a list on all of them. Now you don't have to remember all the elements, obviously. Good luck remembering it. But the point is, these numbers are the number of protons in the atom. We'll discuss what protons are in a few minutes, but for example, 1 is hydrogen, 2 is helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and I'm going to stop here and before I actually it actually says over here what they are. But anyway, these are the various building blocks of everything. Everything that you have, everything that exists, is some combination of all these different types of atoms. They're the elements, which are what atoms are made out of, which are really types of atoms. An atom of hydrogen is the element hydrogen. So atoms are the smallest particles of matter, and they have the characteristics of an element, which means it cannot be broken down into a different substance. Atoms are based on the nucleus, which is the middle of the atom. There are really 3 particles. Hopefully you should remember these. But there are 3 particles in an atom. There are protons, neutrons, and electrons. The protons and neutrons are in the middle. And the only difference between them, well, slight difference in size, but protons are positively charged. Neutrons are not charged, they're neutrally charged, and the electrons, which are outside of the nucleus on the energy levels, are negatively charged. And an atom is neutral, as most atoms are in their natural state, when it has an equal number of protons and electrons. Neutrons obviously don't matter because they're neutrally charged, but if you have 8 protons and 8 neutrons, then you are a neutral element, as it turns out, of oxygen, because oxygen is defined by having 8 protons. So, if you look at the diagram over here, again, fairly self-explanatory. You have the nucleus in the middle, which is the protons and the neutrons, and the electrons kind of float around the nucleus, fly all over the place. The electron cloud, again, is just really another way of saying the space in which the electrons float around the nucleus. So you can see these circles, which are called orbitals, which are kind of like the orbit path of the electrons, similar to the orbital path of a planet around the star. So that's the way an atom is constructed. You got the protons and neutrons in the middle, and you have the electrons floating around on the outside. The atomic number of an atom is the number of protons. In fact, every atom is defined by how many protons it has. An atom with 1 proton is hydrogen. Atom with 2 protons is helium. Atom with 3 protons is lithium, and then beryllium, and etc. So carbon has an atomic number of 6 because it has 6 protons in its nucleus. Any atom with 6 protons is inherently considered carbon. And the mass number, in other words, how big the atom is is based on the number of protons plus neutrons. So if carbon has a mass of 12, that means it has 6 protons and 6 neutrons. Although atoms could have different numbers of protons and could have different numbers of neutrons, atoms always have the same number of protons. If it has 12 protons, it's always magnesium. But it doesn't always have to have the same number of neutrons. The number of neutrons can change. And the same proton with different numbers of neutrons is something are called two different isotopes. So for example, if you have carbon always has 6 protons. If a carbon has 6 neutrons also, fine, it's a carbon with a mass of 12. If a carbon has 8 neutrons, so it would be 6 plus 8, and its mass would be 14. They're both carbons, but they're different isotopes of carbons. So isotopes are atoms with the same atomic number, but different numbers of protons. They're different numbers of neutrons, excuse me. They're different atoms of the same elements. The reason why they're important, or at least one reason, is because some isotopes are more radioactive than others. For example, carbon-14 that has 14 neutrons falls apart, whereas carbon-12, which has 12, does not. An example of an isotope would be if oxygen always has an atomic number of 8, which means it always has 8 protons. One oxygen might have a mass number of 17. Since they always have 8 protons, that would mean 9 neutrons, not electrons. I'm sorry, this is a mistake. I'm going to change it over here. Okay, so it means it would have 9 neutrons. Another oxygen item has a mass of 15. That means it also has 8 protons, because it's oxygen, by definition it has to have 8 protons, but it only has 7 neutrons. How many electrons do they have, by the way? Well, the answer is, generally speaking, things will be neutrally charged, so we'll generally have 8 electrons. And again, this table, which we looked at a few moments ago, is based on the idea that different atoms have different numbers of protons. The number on top is the number of protons they have. So now let's segue that into minerals. Now minerals are made up of different types of atoms. For example, just quartz is made up of silicon and oxygen. Again, you don't have to remember those, but how do you determine minerals one from the other? Well, there are many different ways to distinguish, many different characteristics or possible characteristics of of minerals. One possible way of determining what type of mineral something is by its optical properties. Is it opaque, which means you can't see through it. Translucent, means that you can partially see through it. Light can go through it, but you can't actually see an image through it. Or transparent, where both light and image are visible through the sample. Glass, as we know, is transparent. Most rocks, most of what we think as normal rocks, are probably opaque. That's one possible characteristic of a mineral. Another is luster. How does it reflect light? It could be metallic, reflecting light. It could be dulled. It's a little hard to use it for identification because even if something normally would be metallic, it might be dirty and therefore doesn't look metallic. So you got to be careful about that. Color is not always used as a property to identify minerals, and the answer is because, first of all, some impurities in a mineral can be different colors, and also oxidation, which means rust and other types of weathering, can change a mineral slightly. You could have, for example, orthoclase be pink, and it can also be green. It's the same thing, same mineral, but it could be different colors just based on the different composition of it. You also have streaks. Some minerals have streak. If you scratch it against a plate, will it leave a residue? Gold, for example, has a gold-colored streak. Pyrite, for example, has a black streak. That's one way to tell the difference. Pyrite is also known as fool's gold because it looks like gold, and people who were fools thought it was gold. But if you scratch it against a plate, it leaves a black streak, which gives away the fact that it's not gold. Common crystal shape, which means habit. The habit means how Is it shaped? If I used to do this when I used to teach earth science. I used to take some things that have specific crystalline texture, like calcite or halite or something. You throw it as hard as you can on the floor, and it breaks into 1,000 pieces. And amazingly, all 1,000 are the exact same shape. They may be different sizes, but they're different shape. So some that's called. It's also called cleavage, by the way. And so some different minerals sometimes have cleavage, but on the other hand, some minerals don't have any cleavage. They just shatter into random pieces, in which case that doesn't really help you. Specific gravity is density. How heavy is it per unit? If I take, 1 square inch of the mineral, how much is it going to weigh? How compact it is, how dense it is compared to water. Water is the famous thing that everything is compared to when it comes to density. Water is 1 gram for every milliliter. That's the amount of mass it has for every milliliter of volume. And so rocks are measured against that. As you can probably imagine, most rocks are more dense than water, but rocks can, if that's another way, by the way, to tell the difference between gold and fool's gold. Pyrite's density is a lot higher than, or lower, excuse me, than pyrite. Gold is more dense, so if you have two samples and you don't have a streak plate with you and you can't use the streak and you want to figure out whether something's gold or fool's gold, you can. I think gold's density is something like 20 grams per milliliter, whereas pyrite's is only like 4 or 5 grams per milliliter. So you can tell the difference that way. You also have mineral strength. Its tenacity. How hard is it to break? Its hardness, which is its ability to resist scratching or abrasion. That's, for example, if your fingernail can scratch something, it's extremely weak, or it's not hard, it's extremely soft. Whereas there's actually a scale called Mohs scale, which puts all rocks on a 1 to 10 scale with representative rocks at each level. I think Mohs scale was talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, um, topaz, corundum, and diamond. Anyway, the point is that you can actually see how hard something is by seeing if something can scratch quartz but cannot scratch topaz, it's something like a 7.5. But again, I'm not going to worry about that right now, but the point is that hardness is based on something's ability to resist scratching or abrasion. Sometimes you can identify minerals by whether they can do that. Cleavage, as we discussed before, tendency to break along certain lines. Halite, mica, calcite are examples of minerals with cleavage. Size. Some of them have different size, and there are other factors like, taste, I guess. Halite is actually salt, so it tastes like table salt. So that's one way of identifying it. May not be the best way. You might not want to taste all the minerals that you're testing, but at least it's one possibility. Okay. Now, again, so there are many. The idea over here is that there are many minerals that might have the same characteristics and so therefore cannot be used to identify them. For example, might have metallic luster. Native copper and galena both have metallic luster, whereas fluorite and halite both have brittle tenacity. So if you're going to tell the difference between fluorite and halite, well, they both have brittle tenacity, so you got to figure something else out. You have to maybe figure out their density, etc., etc. Able to cut into thin shavings. Gypsum and talc, both very soft minerals, and so you're able to scratch them and cut them up very easily. Density, and we discussed this before, but also mention it again, is mass per volume. Really, it's the number of grams that the thing weighs, or really is mass, divided by the volume, which is measured in liters or milliliters. Cubic centimeter is actually the same as a milliliter. 1,000 milliliters is a liter, like 2-liter Coke bottles, got 2 of them. So, for example, if you have something has just if you have 1 cubic centimeter, which means the same amount of volume, and substance X weighs 21.7, and Y weighs 4.1, and Z weighs 3.9, that means substance X has a much higher density because it's the same volume, and it's a much lower weight. Much lower mass. So the way you figure out the density is you figure out the volume. In the lab, you would use something called a graduated cylinder to see how much water it displaces, and you would also figure out the mass by weighing it on a scale. Another word for density is specific gravity. They essentially mean the same thing. Here are just some examples that are good to remember. Water has a 1 density. That's the thing that everything is based on. Quartz, for example, is 2.65, relatively low but higher than water. Galena is much higher, and gold, 24 karat gold, as I mentioned before, has a density of about 20, which is very, very high density. Most minerals are what are called silicate minerals. Silicate minerals are minerals that contain silicon and oxygen. You can see over here there is a little diagram of how they work. It's not that important that you remember exactly what these things look like, but what is important is that minerals that contain silicon and oxygen are called silicates. They're the most, I wouldn't say most, but most common. They're more than any other mineral group. Quartz is made of completely of silicon and oxygen, and that's why it's very, very common. Quartz is one of the most common minerals in the crust because, well, first of all, as it happens, silicon and oxygen are the two most common atoms in the crust, and therefore it's common sense that quartz would also have a very high concentration. Some examples of minerals that you see in daily life. Well, diamond and gold, I think we all know what those are. Those are both minerals. Those are both individual well, diamond is actually made from carbon. Gold is its own element. Silver is used for silver objects like silverware and also for, of course, jewelry. Salt to melt snow, halite. Halite is really the same mineral as table salt. They use it in bigger chunks. You can actually eat it, although I wouldn't recommend it, but you can. Pencil lead is made from graphite, which, by the way, is also made from carbon. Again, you can have different minerals, by the way, that are made from the same element. Carbon, they're, two of the graphite and diamond, and also coal is made from carbon, but they're different minerals because they have different properties. Watch faces very often are made with quartz. If you look at your watch, I am actually looking at my watch right now. You can't see it, but it says quartz right in the middle, and because it's the watch face is made from quartz. Quartz is a very cheap, plentiful, and hard mineral, and so can be used for things like putting things together. Magnets are used from iron. And how do you get these minerals? Well, usually you mine them from the ground. There are some problems with mining. The caves and mountains can collapse, avalanches. Mining could cause problems for the environment, and it could also cause health problems for the individuals. Coal miners in West Virginia and places like that very often get all types of lung diseases and can be killed in collapsing mines, and it can be dangerous, but of course people have to mine these things out of the ground because that's the most efficient way to get them. I guess many of these can be created in a laboratory from other minerals, but it's much, much less efficient. It's much more efficient to mine it out of the ground. Chapter 3 builds on Chapter 2. Chapter 2 was about minerals, where we figured what all the earth and the rocks on the earth were made out of, and minerals build into rocks. One of the most common rocks, for example, is granite. You see that all over the place. You also see it sometimes in your kitchen counters. Well, granite is made out of quartz and orthoclase and many other different types of minerals. In other words, you take many different minerals, put them all together, and you have a rock. Rocks could be formed in 3 different ways, and you have an intimidating document that you see over here called the rock cycle, and I'm not going to worry so much about getting you all the specific information that you see down here. I'm just going to kind of give you the 3 and describe them very briefly, what you need to know. You have igneous rocks over here, you have sedimentary rocks over here, and you have metamorphic rocks over here. Igneous rocks are rocks that are made from melting lava or freezing lava. Excuse me. You have a volcanic eruption or deep underneath the ground. You have liquid rock because it's hot underneath the ground for whatever reason, and it cools off, either because you have the volcanic eruption and the lava spills onto the earth and it gets cooled, or because it's underneath the ground but it gets moved by the movement underground to places where it's a little cooler and it refreezes. It becomes an igneous rock. Sedimentary rock is rock that is formed by tiny little pieces like crumbs of rock in a little dirt pebbles get crushed into forming a big rock. Well, that's how sedimentary rocks work. Picture a river, that takes, millions of tiny little dirt particles because it sweeps them off the riverbank. And then where the river stops and it goes into the ocean, these little sediment particles kind of fall down. They all get squeezed together on top of each other until it builds up enough pressure to solidify. Then you have sedimentary rock. Metamorphic rock, on the other hand, simply means rock that has been changed from another type of rock, either by heat, because it's gotten hot, it hasn't melted totally to become a new igneous rock, but it's melted a little bit or changed structure. Pressure can also cause metamorphism. Just to give you the most famous example, diamond is a metamorphic rock. Diamond is caused by pressure. It used to be graphite or coal or something, and then it's squeezed together by something extremely heavy, and that causes all the carbon to kind of condense and get very small and very hard, and what you come out with is a diamond, which is a type of metamorphic rock. If you ever saw Superman 3, Superman takes a piece of coal at the end and squeezes it together and makes a diamond out of it. Now, of course, no human in real life is that strong, but theoretically, coal could be turned into diamond through enormous pressure. And in fact, they do that to make synthetic diamonds. So now let's take a look at some of the rocks. I just showed you the rock cycle. Well, I mean, the reason why there's this cycle, I didn't mention it previously, is that the cycle is that any rock can turn into any other rock. In other words, igneous rock can be formed by rocks melting and refreezing, sedimentary rocks by them getting broken apart and then recoming together by water or whatever it is, metamorphism by heat or pressure. That's all this diagram means. This diagram looks very intimidating, but it really isn't that intimidating. It's just a matter of realizing that's how these three types of different rocks form. Igneous rocks are formed as magma, which is really kind of another word for lava. Magma is below ground, lava is above ground, but it's the same idea. And those really, really hot rocks that are melted. Molten rock is generated by partial melting of the Earth's mantle. Deep beneath the ground, you have really hot areas where you have the plates rubbing against each other. You have tremendous heat that's generated, and then when they refreeze, they become igneous rocks. In order to identify igneous rocks, you do it based on size and arrangements, and these things also can help geologists, namely scientists, figure out where these rocks came from and how they formed. But mineral composition also is, rocks are made of minerals. So rocks are usually made of many different types of minerals that are formed together. This is an example. Again, I don't think you have to memorize these, obviously. It will be very difficult. But these are just some examples of how igneous rocks are classified. You have basaltic rocks, granitic rocks. As you can imagine, granitic rocks are like granite. Basaltic rocks are like basalt, and these are just some different types, and you can see how they are classified. They're classified based on texture, they're classified based on color, they're classified based on which minerals are inside. Granitic has quartz and feldspar, basaltic has pyroxene and plagioclase feldspar, ultramafic has olivine and pyroxene, etc. Igneous can be fine-grained, which means if they cool fast, like for example lava, they're not hard, they become very, like glass is an example of a very fine-grained rock, or they can be coarse-grained, which they form much harder, like much more rocky, and when they cool off very slowly. When they cool off quickly, like for example when there's a volcanic eruption and the lava refreezes, very often it becomes very glassy because it's very, very quick. So and glass is very fine-grained rock. So glassy is a very fast rate of cooling, with the unordered atoms frozen in place without any kind of crystalline structure. That's why lava shatters under 1,000 pieces. Like lava, also underwater lava, things like that. When I used to teach earth science, I had a piece of obsidian, which is volcanic glass, and it's basically black, but it's glass. It feels like glass. It's not it doesn't shatter as quickly as the kind of glass that we used to drink in, but it's the same basic idea. It feels kind of like glass. You also have granite. Granite, of course, is a form of igneous rock, one of the most common types of rock. Granite is composed of light-colored silicates, quartz and feldspar. Silicates, remember, being things with silicon and oxygen. And the reason why it's called felsic is because it has feldspar and silica, that's why it's called felsic. But the only thing that's really important to remember about granite is that it's a silicate, which means it has silicon and oxygen. Then we have sedimentary rocks. Sedimentary rocks are rocks that are formed by little pieces that get broken off, and we're going to learn more about it next chapter, but move from place to place and then get squeezed until they become a rock. They're formed from rock sediments, and the most common form are compaction and cementation. Compaction means compacted. It means get squeezed together. Cementation is it gets stuck together through, sticky materials or water or whatever else. It's compaction, whatever else causes it to come together, and that's how these things form. How are sedimentary rocks formed? Well, there are detrital sedimentary rocks. Detrital means detritus means like little crumbs and little pieces of things. So sediments that are dumped by liquid, dumped by water, dumped by things like that. And the material are in solid particles. They're classified by particle size. How big are the particles? Some common examples: we have shale, sandstone, conglomerate. Conglomerate means a whole bunch, as the name implies, means a whole bunch of different types of rocks that are together. Chemical sedimentary rocks are derived from materials that are carried in a solution to lakes and seas. Solution means it's mixed up with the water. The particles, the little sand particles, little dirt particles, get worked in with the water, and eventually when the water stops running or goes into an ocean, these particles fall to the ground and become sedimentary rocks. Some, again, same. They're classified similarly by mineral composition. And limestone's an example. Microcrystalline quartz, which means quartz that became sediment, that turned into sediments and then recrystallized. Coal is an example. Rock salt, gypsum, things like that. Coal's also an example of a sedimentary rock. Here's a little chart over here. Again, you don't need to memorize these. Just remember what some of these. Number one, what some of these sedimentary rocks are. Conglomerate, which is a lot of different types of minerals put together. Sandstone, siltstone, shale, mudstone. You can see how these things get their names also. Mudstone is when you had mud and mud forms into a rock. If you try it, if you take a big slab of mud and you squeeze it together really hard and you dry it off, it'll get kind of a little bit of a rocky texture. Other types include, limestone, gypsum, rock salt. All these things are made from different minerals. You can see that some calcite, which is over here, is one type of mineral, but it could make many different types of rocks. Gypsum, halite, all these things. You can also classify them based on the chemical origin. You can also classify them based on what their particle size are. Do they have a coarse particle size? In other words, do they have big particles, big little pieces, or do they have very fine little pieces as well? And finally, you have metamorphic rocks. Metamorphic rocks are produced from pre-existing rocks, and they form either by heat or pressure usually, or by some sort of a chemical change. They change from one type to another, and this leads either into changes in texture, which means how it's made up, and mineralogy, what the minerals become. If they get heated up, they could actually change. The atomic structure could change in chemical composition. It could recrystallize, become larger. Some examples: limestone, which is a type of sedimentary rock. If it's metamorphosed, it could actually become marble. Shale becomes slate. Quartz becomes quartzite. As I said before, graphite and coal could actually become diamond if it's metamorphosed. So metamorphism is just a way that rock changes based on heat or pressure or some sort of a chemical change. Now we move into a little bit more of a deeper discussion of the sedimentary process, the sedimentary rock process, and that is really weathering and erosion. Weathering means when rocks break apart and then they have to be moved from place to place. That is called erosion, and then when it gets deposited, that is deposition. That's when it gets deposited. Common sense. All right. How do these things happen? Well, there are three basic types of processes that are, they're powered indirectly by the sun's energy, but you have weathering. Weathering is a physical breakdown of rocks at the Earth's surface, or a chemical alteration of rocks. You could have chemical weathering or physical weathering. We'll learn, some different types of processes of how this weathering happens, but weathering is when rocks break down, which could happen because of physical reasons or of chemical reasons. You could also have mass wasting, which is the transfer of rock downslope under the influence of gravity. Like, for example, a mudslide or an avalanche. Well, an avalanche is usually when it happens with snow, but when it happens with rocks, rocks fall down the hill. That is wasting. And erosion is when it gets moved from place to place, the physical removal and transport of the weathered rock by a mobile agent. That could be water, usually water. It could be wind, could be ice, like in the case of glaciers, where glaciers move south and drag rocks along with it, but that is erosion. So let's look at it a little bit in more detail. And let's start with weathering. Weathering can be chemical or mechanical. Chemical weathering involves chemical transformation of a rock and usually happens in a warm, humid climate. And there are a few reasons for that. Number one, water is an excellent dissolver. Water is sometimes called the universal solvent because water dissolves things very well. So chemicals transport better to get to the rocks in order to weather them in a humid climate. And also chemical reactions tend to work better in warm areas than in cold areas. If you ever played with a chemistry set as a kid, you probably didn't because you were by the time you were a kid, the chemistry sets probably had gotten very weak because they were afraid of being sued. When I was a kid, they had better chemistry sets. But all right, that's neither here nor there. Very often they told you in order to do some certain types of experiments, you were going to have to use a fire, and that's because heat generates chemical changes. So water is the most important agent because water brings the chemicals and dissolves chemicals and brings them to the rocks. So but chemical weathering is more common in warm, moist climates. Mechanical weathering is physical breaking down, and we're going to see how this works. But physical breaking down of rocks, which could happen with chemical weathering or instead of chemical weathering, is when somehow the rocks get broken down into little pieces. So let's take a look at some examples of mechanical weathering. One possibility is frost wedging or frost action. Now frost action is what I like to call the pothole effect. It becomes a lot easier to remember because what happens is the water seeps into the ground and then freezes, and when water freezes it expands, and as it expands it breaks apart the rock, and then when it melts, when it comes springtime or when it gets warmer, well then you just have the hole left. That's how potholes happen. Potholes are much more common in cold weather and in wet weather than they are, for example, in the desert where it's warm and dry. Mechanical weathering in general happens more in cold weather and in wet weather for that reason. Water seeps in, freezes, expands, breaks apart the rock, and then the rock becomes weathered. You can also have crystal growth if you have salt water near an ocean, or if chemical deposits turn regular water into chemical water, salt water. You have salt water fills the space in the rocks, then the water evaporates, and what do you have left? The salt crystals, which are sitting there in the middle, and the crystals grow larger and weaken the rocks by making first little tiny cracks and then enlarging the cracks. So this type of weathering can happen from salt meant to melt snow and ice during the weather. Same thing, when you put salt, I tell my wife sometimes that it's not a good idea to put so much salt in the driveway, even though it helps with melting the snow and helps you get out a little bit easier. The more salt you put on the driveway, the worse it is for the driveway. And the reason is because when you melt everything, first of all, the water itself could seep into the driveway, but aside from that, these little salt crystals can seep into the tiny cracks in the driveway and the rocks or whatever it is, and as they expand, because they get warmer, or as they expand because they grow, because more salt gets formed, they kind of crack the driveway or the rock or whatever it is. So it dissolves into the water and seeps into the crack. Then when the water evaporates, the growth of salt crystals breaks the pavement, and that is how potholes are formed. You also have sheeting, which are fractures in fresh bedrock. And that very often happens because of the reduction in pressure when other rock is eroded away. In other words, sometimes rock is being held together or held in place by other rocks, and when those other rocks are taken away, it kind of destabilizes the entire system. You also, of course, have biological activity. Roots growing, plant roots, tree roots are some of the most effective types of mechanical weathering. The roots grow, or you have decaying organisms, human activity, other animals that burrow, that dig in the rocks, dig in the mud or in the dirt, and that of course causes weathering as well. Okay, so now those are the two types of weathering, chemical and physical, and I think I discussed this before also, but in terms of climate, you have to look at two basic things, temperature and moisture. The more the warmer it is, the more chemical weathering there will be. The colder it is, the more physical weathering there will be because of the frost action. Both types of weathering occur much more in in warm climates. I'm sorry, in damp climates and wet climates than in dry climates. So the more optimal the environment, the faster the rate of the growth. And in dry regions, weathering is slower than in areas of moisture because water takes things away, water breaks things down, water does all sorts of transfers of materials. Okay, so advanced mechanical weathering aids chemical weathering by increasing surface area, which means if you have more physical weathering, which means the rock breaks apart, well then more of the rock is exposed to the chemical elements. So one type of weathering actually helps the other types of weathering, and also human activities can influence the composition of the atmosphere, which impacts the rate of chemical weathering. If humans release pollutants or chemicals into a river or into the area, that tends to change the chemical composition and could increase weathering. And again, this is kind of review, but let's look at this. Climates with higher humidity and abundant moisture are more likely to have weathering for all the reasons we discussed before. Mechanical weathering is made more by cold and wet conditions. That's really frost action, like in Alaska or Greenland. Chemical weathering is helped by warm weather and moisture, like lush vegetation, the root action of the plants that are grown break apart the rocks. So warm, moist places like California are likely to have chemical weathering. In dry places or arid places, which means dry or frozen places, there's very little chemical weathering. And while sometimes weathering is a bad thing, sometimes weathering is absolutely necessary. In fact, weathering is really necessary for life in general because weathering is really the only way you can form soil. What is soil? Well, we all know soil is a place where you plant plants. Plants need soil in order to survive. Their roots need to be able to get the water from the soil, and so the water needs to be able to fall into the soil and penetrate the soil. And without weathering, there wouldn't be any soil. Really, all soil is a bunch of pieces of rocks that were broken down by weathering. Or regolith, which means rock and mineral fragments, little tiny pieces of rocks and minerals, and these things become the well. A regolith is kind of like in between a soil. It's not quite soil yet. That's when the rocks are partially broken down, and you have rock fragments and mineral fragments. When they get totally broken down into like muddy type, not quite mud, but you all know what soil looks like. I don't think I have to describe it. Soil is a combination of minerals, matter, plant matter, whatever it is, water, air, and it of course supports the plants. Adding water to clay-rich regolith or soil, in other words, materials, broken down rocks, weathered rocks, obviously this helps the weathering along, and therefore makes it more conducive to soil. It lowers the strength of the cohesion of the soil, allowing it to break down more, dissolves the bonds in the soil, helps break little holes in it, which cause crevices, little cracks to grow, and the soil is this causes mass wasting, which means the soil flattens out. Mass wasting sounds like a bad thing, but it's necessary because ultimately you want to have a flat ground. The best farms are flat, so gravity allows the soil to eventually even out. So let's finish up our discussion of soil and weathering with also a general discussion of what affects soil. Climate, the wetter the climate, obviously the better soil it's going to form. Warmer climate tends to form soil. The ground doesn't freeze as much and there's more chemical activity. Plants and animals, of course, are necessary for soil. That they eat the vegetables on top of it, they dig in it, all sorts of activity. Time is obviously necessary for soil to form. A lot of time has to pass as the rocks break down. The parent material is, of course, the source of the material matter. In other words, the parent material of soil means the rocks that were broken down to form this soil. Steep slopes, angle matters. Steep slopes have poorly developed soils. So, because the best way for a farm, as we discussed before, is to have flat, and eventually, of course, mass wasting is going to cause things to flatten out. But you want when it rains or when you have something falling in, you want it to go through all the soil relatively evenly to break down the entire soil. On a hill, it's not going to happen. On a hill, when it rains on a hill, what's going to happen? The water's all going to flow down the hill. It's not going to go. It's not going to seep into the soil as much. Whereas if it were flat, it would seep in. Orientation is also relevant. Temperature, moisture, these are all things that we discussed that are relevant. North-facing slopes, for example, and this is just one example, are more likely to be moist and heavily forested than south-facing slopes for a very simple reason. The sun is in the southern sky, at least in the northern hemisphere in the United States, and so therefore, if the sun beats down, then it's going to evaporate more of the water. Whereas in the northern-facing slopes, where the sun is not beating down on it as much, it doesn't have as the water doesn't evaporate as much. If the water doesn't evaporate as much, it's more able to affect weathering and the development of soil in general. Soil also gets eroded, which means soil also gets swept away by rivers, by wind, by whatever. It depends on the characteristics of the soil. If it's mature soil with lots of trees in it and it's solid, so it doesn't erode as much. It also depends on the climate. Obviously, the more moist it is and the warmer it is, the easier it's going to be to erode. And of course, the slope, as we discussed, and the type of vegetation. Trees that have really strong roots tend to stabilize soils. You know, if you put out a brand new piece of soil in your backyard or in a garden or something like that, if you don't want them to get eroded, the biggest risk for it to get eroded is the first few weeks before anything starts growing. Once it starts growing and the roots start taking shape and the roots start, kind of making it more stable, it becomes much more difficult for the soil to erode. Then, of course, you have mass wasting, which we discussed is just a way that the soil evens out, because the soil towards the top of the hill slowly or quickly slide down the hill and kind of flatten the entire thing out. The downslope of rock, regolith, again, which means the broken pieces of the rock, and soil is under the controlling force of gravity. It doesn't require any transporting agent because things roll down the hill by themselves, but it could take a long time. What does cause a hill to start, the soil in the top part of the hill to actually start rolling down? Well, it could be saturated with water, which adds weight and makes it more likely to start rolling down the hill. And it destroys particle cohesion. It breaks apart the particles, which make them more susceptible to gravity. Also, if it gets overly steep. The steeper the slope is, again, this is pretty much all common sense. The steeper it is, the more likely it is to go down. The stable slope is called the angle of repose, which means how narrow does it have to be in order for it to be stable. The steeper it is, the less likely it is to be stable. After a mudslide, well, then you look at the new angle after the material from the top of the hill has slid down the hill, and now you hopefully have something that's a little bit more stable. Also, removing of anchoring vegetation. Vegetation keeps things more stable, so if you remove it, you're more likely to get mudslides and mass wasting. And, of course, ground vibrations from earthquakes, or whatever else would cause ground vibrations. Common sense are more likely to cause things like mudslides. What things are moved in mass wasting? Debris, which means little pieces of rock, mud, earth, rock. How do these things move? Again, this is really pretty much all common sense. They could fall down the hill, they could slide down the hill, they can flow down the hill like a viscous fluid. If it were mud, it could kind of slowly move its way down the hill, and the rate of movement could be either fast or slow. You probably could have figured that out anyway. What kinds of mass wasting are there? Well, one type, the most dangerous type, are avalanches, rock avalanches, or mudslides. Rock and debris hurtle down the slope at high speeds, like 125 miles an hour. It sounds pretty quick, right? The high velocity speed causes the avalanche to just basically it's almost like a fall. When you have an avalanche, the rocks are coming down so hard, it's almost like they're falling. Earthquakes, which can, even if you had a stable hill, an earthquake can cause it to become unstable by throwing it a little off kilter. You also have slump, which of course is a little bit less dramatic than rock avalanches, but still cause hills to get flattened out. A block or blocks of unconsolidated regolith, again meaning broken up pieces of rock, rapidly slide down the hill along a curved surface. This happens when the slopes are overly steepened, and they kind of have to flatten out in order to stabilize. Not as dramatic as an avalanche, but also pretty quickly. Now we're going to get to the ones that are slow. These were the ones that are fast moving, rock avalanches and slump. Now we're going to look at the slow processes. You have creep, which, well, it's pretty much as it sounds. The gradual downhill movement of soil and regolith has the slowest rate of moment, and it causes fences and utility poles, if there are, to kind of tilt a little bit because the rock underneath it is sliding down the hill. Eventually, obviously, if there's a utility pole or a fence that's built into it, eventually it'll come down if the rock underneath it moves. Okay, then you have solifluction, which means very slow movement is the slowest one, in areas underlain by permafrost. Permafrost means permanently frozen ground, like in the tundra, at least the areas that are very cold. The upper layer becomes saturated and slowly flows over the frozen surface below. If you have ice, let's say this area over here in this little diagram, I'll move it over here. In this little diagram, you have this area is permafrost, which means it's always frozen. The layer on top of it that's not frozen, if it's a hill, can slowly move down the hill over it. What causes mass wasting? What can cause these things to move down the hill? Well, heavy rains or snow, again, adds weight to the material and makes things slick. Like you add water to anything, it makes it more slick and makes it much easier to slide. You have over-steepening of slopes. If the slope becomes too steep for whatever reason, material gets deposited on the top of the hill that makes the hill become too steep, and that causes mass wasting. And there's a lot of this is review. Again, you'll see these slides tend to repeat each other sometimes. The maximum angle that is stable is again called the angle of repose. If the hill gets more steep than the angle of repose, then of course eventually you're going to have some mass wasting. Okay, if a slope is unstable, loose bedrock will cause a downslope. It could be by creeping or solidification, whatever that word was, or of course it could be through slump or avalanches. It could ground vibrations from earthquakes. It could also happen when layers are inclined, which means they're on a hill, etc. So again, these are all things that can cause mass wasting. They could be geographic or they could be biologic. They could be just not based on life activity. Biologic means based on life activity, or it could just be on geographic factors. Geographic factors include things like with less trees and other vegetation, more likely to slide, again, as we discussed before, less stable. Dry mountainous areas, such as Southern California, is where I guess there's no inherent reason why that would have mass wasting, but you could, more than anything else, but you could have mass wasting there. Seismically active areas, which means there could be earthquakes, areas that get flooded, areas where you have a lot of rainfall. These are all things, places particularly likely to have mass wasting. Biologic, of course, is when you remove anchoring vegetation. Roots and plants stop or prevent mass wasting. Plants shield the ground from erosion. They lessen the rainwater because the plants absorb the water, and so therefore there's less water to make the ground slick, less water to make the soil heavy and slick because the plants are absorbing it. And so these are especially helpful in preventing mass wasting. And forest fires and mass removal of trees increase mass wasting. I mean, there have been lots of stories that you hear about, because if areas are deforested, which means they cut down a lot of trees in the area, that tends to cause avalanches, mudslides, and all sorts of problems. There was a story, I think, in South America where an entire village basically got mudslided in because the trees were on a hill, and people came and chopped down the trees to use for paper or whatever it is, and that caused the ground to become unstable and caused a massive mudslide that basically buried the village. And finally, what geologists very often do is they look to make a determination if an area is going to have mass wasting in the future or even had it in the past. If you look at old maps or date the existing rock, in other words, you can make a determination, was there mass wasting in this area? In other words, was this rock that's sitting here now at one point or another on top of that hill? If you look at an old map and you see this used to be a hill and now it's not a hill anymore, well, now you know there was some mass wasting, some gravitational flattening. You can drill for sediment and date the existing rock. In other words, see where the rock originally was or what it goes with. If you see some rock on over here, if you see it similar to a rock that was on the top of the hill, a couple of meters over, well then it indicates that this one probably sunk at one point or another. You check the area's general weather. You can look at the cross section of the rock soil in that area. Again, as I mentioned before, what this really means is that you look to see, is this rock at on sea level comparable to rock that was 20 feet above sea level on the next block over, which indicates this thing was probably also 20 feet above sea level at one point. It probably formed at the same time as the other one, but at some point this underwent some sort of a mudslide or other mass wasting. Okay, also you look at, are there faults in the area? If there are faults, you're more likely to have had mass wasting. What type of rock is it? Is it strong rock or is it weak rock? Weak rock, of course, is more likely to have been affected by gravity. How are they situated? What's the orientation of it? Is the rock sideways, which indicates it was all placed there as sedimentary rock, or is the rock kind of at an angle, which indicates that it wasn't all placed there at this, it was placed. If sedimentary rocks usually form when they're flat, so if this thing is not flat, it probably some sort of a hill formed at one point or another. Has been run over by a glacier, which causes different characteristics, and various other similar questions over here that are relevant to making a determination of mass wasting that may have occurred in the past. Next, we're going to look at the hydrologic cycle, which sounds complicated, but it really is not. Hydrologic, is you probably look at you can see the root of the word hydrologic is hydro, and hydro means having to do with water. So another word for the hydrologic cycle is the water cycle, and in this chapter we're going to cover the water cycle, and we're going to cover various other things that relate to water, such as streams, rivers, and that sort of thing. The hydrologic cycle is the circulation of Earth's water supply. The thing about the Earth's water supply in general is that it does not really increase or decrease, save for tiny little amounts that are maybe converted into other forms of matter. The vast majority of the water supply stays on Earth. Even if you drink it, eventually it's going to make its way out of your body and back into the atmosphere. Even if it rains into the ocean, eventually it's going to evaporate from the ocean back into the atmosphere and come back down, and that's the idea of the hydrologic cycle. Water is constantly moving between the oceans, the atmosphere, the solid Earth, the biosphere, namely the living things inside the living things of the body. The cycle is worldwide, and it's powered by energy from the sun, because the key way in which water moves downwards is, of course, rain, but the key way in which the water moves upwards is evaporation. And in order for evaporation to happen, you need, of course, the energy from the sun. This is a simple diagram of the hydrologic cycle. You have evaporation. Now, in this diagram, the arrow happens to be coming from the ocean, but evaporation happens from land also. Puddles, as you might notice, if it rains a day or so later, the puddle might be gone, and the reason is because it evaporated. It was evaporated from the heat generated by the sun, of course. So this is a simple manifestation of it. Evaporation into the air. Eventually, when enough water evaporates into the air, the clouds form, the clouds become darker, the clouds become heavier, and eventually you have rain or precipitation. It could also come down in the form of snow, sleet, whatever, but the point is precipitation comes back to the ground, and then you have the water in the ground in lakes and rivers, and also they run off back into the ocean. Rivers will run into lakes or oceans or whatever it is, and that's the pretty simple components of the hydrologic cycle. But now let's look at it in a little bit more depth. We will look at the different processes. Precipitation is when water falls to the earth. Again, that could be in the form of rain, snow, sleet, hail, whatever. Infiltration is when the water soaks into the ground. When it rains, unless you're talking about hard pavement, the water will seep into the ground. If it's grass, the grass becomes muddy because the water seeps into the ground. Beneath the ground, you have a layer, something called the impermeable layer, where you have bedrock that the water cannot get further down in, and so the water kind of seeps all the way down until it hits this hard bedrock where it can't go any deeper, and that is called the water table. It doesn't say on this slide, but the water table is what people use for wells. When you dig a well, you're not digging a hole just so that rainwater should fill the hole. What you're doing is you're digging all the way down until you get to the bedrock, until you get to the water table, and you're drawing water up from the water table. Then you also have runoff. Runoff occurs, first of all, when the ground is hard enough so that the water doesn't penetrate, like streets and pavement and things like that, but also when you have excess water, when the ground is already soaked, when the mud is soaked, so any water that falls on top of it just sits on top of the ground. If it's at the lowest level of the area, well, then it just sits there. But if it's at a higher level, then gravity causes the rain water to kind of run downhill to the lowest point. We've all seen this happen a million times after a rainstorm or on a day when snow is melting. If you walk on a hill, you can see on the side all the streams of water running toward the sewers. That is just a manifestation of runoff. Common sense. Evaporation is when liquid turns into water vapor and evaporates from a lake or from a puddle or from a stream or from an ocean and goes up into the sky to form clouds. Transpiration is really the same thing as evaporation, except that it is from plants into the atmosphere. A plant might have water, and if a plant does have water in it, it has to in order to survive. If it's hot outside, some of that water may evaporate into the atmosphere, and the combined effect between evaporation and transpiration is sometimes called evapotranspiration. Sometimes in science texts, on exams, you'll see the word evapotranspiration, and it sounds very complicated, but really evapotranspiration means the same thing as evaporation, except it's not just from streams and puddles, it's also from the water in plants. And water could be liquid water, or, as you all know, water could be stored as ice in cold areas, either high elevations, high latitudes, which means further away from the equator, or even relatively low latitudes, in the winter. If you live in the New York area, New York is only about 41 degrees latitude, closer to the equator than it is to the North Pole, and nevertheless, in the winter months, very often you have ice that is stored on the ground. The water doesn't immediately soak in or run off or evaporate, and again, this applies whether it fell as rain and froze, or fell as sleet, or fell as snow. Either way, it could remain as ice or snow on top of the ground. Water is stored as ice, like in snow fields, in other words, fields covered with snow, expanding ice sheets, and glaciers. What a glacier is a huge ball, a huge thing of ice that expands when more snow or more rain or more precipitation freezes in it. It kind of expands southwards. I mean, picture an enormous ice cube that's in a freezer. If you add more to it and it freezes and it expands, sooner or later, if it gets big enough, it's going to expand outside of the freezer. It's going to bust open the freezer and go outside. Well, the same thing is true when you're talking about glaciers. As they keep expanding because more frozen water keeps moving into it, they tend to expand southward into warmer areas until it reaches a point where it melts. Obviously, if the colder the Earth is, the further south these glaciers are going to get from the North Pole. So glaciers can store large amounts of water on the land because instead of dripping and running off and melting and falling back into the ocean, it will stay on the land as frozen water. This I just I just thought to put a picture of a glacier that I was in Alaska a couple of months ago and I saw a glacier called Byron Glacier, and this is Byron Glacier. I wanted to show you something very interesting. This is Byron Glacier in the winter or in the spring where it's at its maximum, where there's a lot of ice and snow that is taking up the glacier. And this is a picture of that same Byron Glacier, but in the summer. And in the fall, it's also smaller because it's had the whole summer season to melt. So you can see the difference between what we just saw, a spring or winter picture and a summer picture, where it's the same glacier, but it's much smaller because there's been a lot of melting over the course of the summer season. And the last thing, when there are a lot of glaciers, in other words, when things are very cold, it causes the sea level to drop because there's more water on the land instead of the sea. On the other hand, as we'll learn later on, when you have glaciers melt because there's been, global warming or something like that, well, that causes the sea levels to rise because there's less water stored on the ground. Remember, there's the same amount of water altogether. So if more of it is stored on the land as glaciers, so less of it is stored in the sea. More of it is stored in the sea, less of it is stored on the land.